So now let's consider the impact that the nucleophile has on our SN1 and SN2 reactions. So for SN2 reactions, the nucleophile is super important, and we need a very strong nucleophile. Most of the time, if not always, you're going to think of a nucleophile that is going to carry a negative charge for your SN2 reactions. For SN1, your nucleophile doesn't really matter as much. If you remember from our kinetics, in SN2, the rate of the reaction equals a rate constant times the concentration of your nucleophile, concentration of your R leaving group or your substrate. For SN1, it is just of your substrate, and your nucleophile does not even play any part in the actual rate determining step. So for SN1, it is actually okay if weaker. And because of the fact that in some cases you can have some competition, and that's going to be what we're going to be building up to, competition between SN1 and SN2, a lot of times you will actually see weaker nucleophiles favor your SN1s because they can't go through an SN2. They're not strong enough in order to do that kind of backside attack. Now, we've talked a lot about bases, and there's a lot of similarities between bases and nucleophiles. However, the term basicity and the term nucleophilicity, describing the strength of a base or the strength of a nucleophile, are not interchangeable. And that's something that a lot of organic chemists sometimes interchange, but I do want to go ahead and kind of formally define here. If I use the word basicity, we are talking about how strong or weak your material is at abstracting a proton. Nucleophilicity is not focused on a proton, but an actual attack on an electrophilic carbon. So nucleophiles and bases don't necessarily trend in the same direction. They can parallel, but it's not a one-to-one. In many ways, you'll kind of see, as I kind of have here in bold, not all bases are good nucleophiles. If something has a really high amount of basicity, it might be more often that it actually abstracts a proton rather than attacking your carbon. So there's kind of this balance between basicity and nucleophilicity. So what we're going to do is we're going to kind of walk through a series of kind of 4 general themes. I have the word rules, but I think themes is maybe a little bit better here, to describe the strength of nucleophiles. And we'll give some examples for each of those. So our very first one is, if you have a negative charge, you're going to be better than something that is neutral. So we are generally going to be looking for things that carry negative charges. An example, for example, that we've kind of seen already, hydroxide is going to be a better nucleophile than water, for example. Similarly, a lot of times you'll see, especially in like solvolysis-like reactions, if you have, for example, a protonated carboxylic acid, that is going to be weaker than a deprotonated carboxylic acid. So if you're trying to rank or think about things that make a better nucleophile, carrying a charge is going to be one of the go-tos. And often if you're trying to decide, is this my nucleophile or is this my substrate, if it carries a negative charge, chances it's going to probably be your nucleophile. Now, one thing that we'll do a decent amount, and I think you've already kind of seen a little bit in our last class, is doing some comparisons and thinking about the relative rates between multiple different reactions where you just change one component. And if you're comparing based on your nucleophile, if you are in the exact same row of the periodic table, your strength is going to increase in the same way as a base. So nucleophilicity is going to decrease from the left to the right, following your trends in electronegative. So less electronegative equals stronger. More electronegative elements are really tightly bound with those electrons, and they're therefore less reactive. So if we were considering maybe some nitrogen versus oxygen versus fluorine, a NH2 with a negative charge is going to be better than an oxygen with a negative charge, which is better than a fluorine with a negative charge. So the kind of key idea here is your less electronegative is going to give you stronger values. Same thing, like if you're comparing, like instead of having negative charges, if you had maybe ammonia, NH3 versus water, the nitrogen is going to be better than the oxygen. You could do the same thing, like if you're comparing like maybe a phosphorus and a sulfur, phosphorus is going to be better, so on and so forth. The next is going to be thinking like the opposite kind of direction on the periodic table. So instead of thinking about a row, let's think about a column. Your nucleophilic strength is going to increase as we go down a column. And it's going to be based on size and polarizability. So bigger atoms are generally going to be stronger. So if we wanted to think about maybe our halogens, iodide is going to be better than our bromine or bromide, which is better than our chloride, which is better than our fluoride. And you'll see in both of those, fluorine being the kind of worst. So as we get less negative and bigger, you're going to be a better nucleophile. Finally, the last thing that we'll kind of consider is the size of everything else. So the discussion of size for number 3 is purely based on an individual atom. In the second one, which just seems a little bit contradictory, but it's not, the second one is the size of everything else that's not the atom. So steric bulk actually makes things worse nucleophiles. So if you would consider an oxygen, and maybe let's consider an ethoxide. So we have an ethyl group and then an oxygen. And we're comparing that to maybe, let's say, a T-butoxide, where you have a big, bulky extra stuff. That extra bulk is going to get in the way. So if you're trying to do a nucleophile and come in and attack, if you have big, massive, bulky stuff coming behind you, it's a lot harder to fit into a spot, and therefore it's less likely to be able to actually be a good nucleophile. So in general, less bulky, not corresponding to an individual atom like number 3, but the entire molecule will help you be stronger. And these are kind of some 4 kind of key criterions that we're thinking about when we're thinking about what makes a good nucleophile. And when we're thinking about strong nucleophiles, we're really thinking about SN2. If you're comparing 2 different species, and like for example, like these 2 at the end, if one was going to go SN2 and one was going to go SN1, the one that's going to be a stronger nucleophile will favor your SN2.